Okay.
Oh, fantastic.
Okay. Last things to do. Okay, let's talk just a little bit about bonding. The only thing about bonding that you've done so far is the Lewis structures. Okay, and then the Lewis structures, you just show how the electrons are drawn, and the electrons that you work with are, of course, the valence electrons, right? So you just show those electrons, and that's it, pretty much. So, for example, if you have hydrogen, and remember this is only for covalent structures, okay? Yeah, something happened, didn't it? Yeah. So far away. Only for covalent structures where you have overlap, okay, of electrons. That's the only place where we can talk about what I'm going to talk about now. So when you have hydrogen bonded with hydrogen, okay, the way you show it is this, okay, but in reality, if you think about it, this is not the real structure, okay, the way it goes. The electrons in the hydrogen that are overlapping are S1 and S1. Is everybody okay with that? Okay, that was the electronic configuration for hydrogen, and specifically 1s1, 1s1. Okay, that's what it is. 1 doesn't matter because it could be in any shell. The important thing is that you have s electrons and s electrons, okay, that are overlapping, which means that when you draw this out, it will look something like this because each of the s electrons have spherical shape. That's a hydrogen-hydrogen overlap. If you were talking about a chlorine-chlorine overlap, that would be what kind of orbital overlap? P overlap. Okay, so this is P and P. And so when you look at the electrons, they will probably be like a dumbbell shape like this. So it's at a P and a P overlap, okay, over here. It's not the same as SS overlap, okay, and that has to do with the shape of the orbitals. And all you have to do is, when you look at these things, is look at where the elements are in the periodic table. Are they in the S block, or are they in the P block? Okay, and then determine what it's going to be. So if you had something like HCl, here your overlap is going to be SP overlap. Good? Okay. Now this is very nice. It looks very simple enough, okay? And this is still Lewis structures, okay? This is still pretty much Lewis structures. Now if I were to take something for methane, okay, CH4. For CH4, I have carbon, and carbon is 1s2, 2s2, 2p2. And hydrogen is 1s1. So now when I look at the orbitals, again looking only at the valence shells. Okay, so when I look at the orbitals now, for carbon, I have 2 s orbitals, and I have 2 that are going to be dumbbell shape. Is that good with everybody so far? Yes? Okay. Hydrogen is 1s1, okay, which means that it's only the s electrons. So if it's only the s electrons, then this is what hydrogen is going to look like. That's the overlap. And how does this structure look? Does it look good, weird?
Looks unbalanced.
Looks a little unbalanced, doesn't it? Looks like that you might have a different overlap here, a different overlap here, which means that we're talking about different maybe bond energy and bond length, okay, things like that. They would be different for these 2 bonds and these 2 bonds. But the thing is, that's not what happens, okay, because all these bonds are supposed to be equal, okay? So which means that the Lewis theory is not able to explain everything, okay, that goes on in the bonding. Are we good so far? Okay. Which is why we have the valence bond theory then. Okay, in the valence bond theory, we take the bonding to the next level and say, okay, how can we explain this fact? Okay, where you have S and P overlaps going on very differently. So valence bond theory is also known as hybridization. And hybridization is, as you would say, the normal term, where a hybrid is a mixture of things, right? Okay, so that's exactly what happens here also, is you have a mixture of orbitals, okay? Instead of mixing technologies or anything like that, here you would mix orbitals. So I'm going to go ahead and take methane for you first. And hopefully once I show methane to you, the rest of it would be a lot easier and faster to go by, okay? Because only I have limited time to do everything today. So again here, I will take only the valence shell, okay, which is the 2s2, 2p2. And when we talk about hybridization, by the way, it's only for the central atom, okay? We don't talk about the terminal atoms. The terminal atoms will not have hybridization, only the central. So if you have two central atoms, both of them can be hybridized, okay? Differently, similarly, whatever it is. So now I'm going to take this a little bit different, okay, and draw the diagram out. Here's the energy level, and here is like a box configuration, but not quite box, because I'm also showing the energy over here. So here is my S, here are the P, okay? Remember there are 3P, X, Y, Z, okay? And then here's the S. So in the S, I have 2 electrons, and in the P, I have 1 electron each. That's how you would fill out for the box configuration, okay, for carbon. Okay, over here, this is called the ground state, and you can call that GS for shorthand if you want to. When bonding has to occur, you have to provide energy, okay, to an atom. When it has energy, it starts getting excited. And so you have an excited state, and in the excited state, short form ES, you can have electrons jumping around, and so one of these electrons from the S will go on to the P over here, because that's empty and that's available. So you have now 1 electron in each of the orbitals. In the ground state, you don't. Okay, in the excited state, you do. And now comes the hybridized state, because this is where hybridization occurs. Hybridized. So here's what is happening in the hybridized state. You will take one of the S over here, and then 3 of the P. So you will take all of these and mix them up, okay, very nicely. Now, if you remember when we talked about orbitals back when, chapter 7, 8, I mentioned to you that when you want to imagine these electrons and how they exist, I would like you to imagine them as a cloud, okay? And that's the best way, because if you visualize it that way, it will make everything a lot easier, okay? So if you visualize them as clouds, and if you visualize them as just spaces where electrons can exist, okay, then it will be a lot easier for you to visualize this. So here we are taking one of the S orbitals, and we are mixing it with 3 of the P. So the P orbitals are all dumbbell. They may be going in different shape, in different directions, okay, but they all have the same shape. Okay, so you're taking all of these 3 and you're mixing them up nicely. Okay, so when you mix them up, they all become kind of one. So here you have, let's say, 1 big orbital, and because you have 4 electrons, all of this will have to slice into 4. Okay, because you have 4 electrons. So let's take this and you slice it into 4, 1, 2, 3, 4 equal orbitals, because you have 4 electrons, okay, in there. So you slice it into 4, and by the time the orbital comes out then, okay, and divides into 4, you will still have the dumbbell shape, but you will also have some spherical character in it, okay, so which means that the dumbbell will just get a little chubbier. So you have 4 orbitals now, and if you can, try to draw at least one of the lobes a little bit fatter, because that's got the spherical character to it. And that's called hybridization, okay, where you take different types of orbitals and you mix them together to get new orbitals. Okay, so a few things over here, and if you understand this one well, then you should not have problems with later on. So make sure you ask me questions now if you have any. So here we are mixing S P, P, and P. So which means that the final orbital mix over here, the hybridized, it's called SP3. So you have one S and 3 P orbitals in there, okay? So which means that you have a total of 4 orbitals, right? Because you have S and then you have the 3P, so you have total of 4. That's the first thing, okay? The second thing, and this is a question for you, is they are all equal, okay? That I'm telling you already, okay? They're all equal, but my question to you is, what is their energy level? Okay, so you have P here, which is higher energy than S. We already know that, okay? Back from quantum numbers, that P is going to have higher energy than S, but the question is that now I have the hybridized orbitals, okay? The new hybridized orbitals. So what is the energy of that? Is that going to be higher than P? Is that going to be the energy level of P? Is that going to be in between S and P? Is it going to be the energy level of S? Or is it going to be lower than S? So in the 5 numbers, pick one. 3? Okay, and you're very good, okay? Very correct. So it should be in between the two, okay? Because you mix the P and the S, so it should be in between, and I'm not saying it's exactly in between, but it's in between, okay? Somewhere. So now I have to show 4 orbitals, so I'll just draw the 4 lines, each of them with 1 electron each. They're all at the same energy level, they're all the same shape, and they're all sp3. Are we good so far? Okay. The hybridization or the valence bond used to be a theory, but very lately in the last 5-7 years, they've actually proven it to be true, okay? So it's, this kind of a model does not exist anymore. The Lewis theory, that model, we know it does not exist, okay? For a lot of molecules, because we know hybridization occurs, okay? That's for sure. So this is really what we have now. So which means that now my carbon looks very different, okay? So my carbon now has these 4 lobes that look very much the same, okay? Unlike what I had before with the S and the P, I still have the 4 hydrogens, so that's still there. And so now this is the new structure that I can draw out using the orbitals. It looks much nicer. No? Come on, Max. A little bit. Just a little bit. Okay. A lot better? Actually, a lot better. Not just a little bit. A lot better, okay, than what we had to begin with, okay, over here. Okay, so that is what we call SP3 hybridization, because we mixed 1 S orbital with the 3 of the P, okay, orbitals. Okay, now I'm going to make it a little simpler, because my question generally for you when we get into the exam is going to be something like, you know, here's a molecule, what is the hybridization on it? Okay, so how do you figure that out? All right, so the way you would do that, because there are certain things that don't change, okay, for this molecule. So for first of all, what is the Axe formula for this? Axe formula. AX4, that has not changed. So it's still AX4, which means that the geometry is?
Tetrahedral.
Tetrahedral, just tetrahedral. The shape is? Tetrahedral. And that's tetrahedral because you have 4 atoms in there, okay? 4 terminal atoms. So the geometry is the same as the shape. What's the bond angle? 109. So did anything change about methane as such? Did any of the properties change? No, none of it changed. So all the properties remain the same. The only thing that changed is how we look at the bonds. Okay, that's the only thing that changed. Everything else is the same, which is a good thing. Okay, at least nothing else changed about it. Are we good so far? Do you have any questions about any of this? Because the next 2, I'm going to go really fast. Anything about the mixing of the orbitals? Anything about the new energy level or the new shape? Good. So this is SP3 hybridization. We also have SP2 and SP hybridization. Okay, so there are 3 hybridizations we generally talk about. So let's do SP2 now. And for SP2, I will take BH3. And remember, I'm going forward right now, okay, which means that I am giving you the example, okay? I'm going to tell you later on how to actually go backward and figure it out yourself, okay, how to figure out what hybridization it is. So boron is what we're looking at, and boron is right there, so 2s2 and 2p1, 2s2, 2p1. Okay, we're going to do this really fast, so if I talk a little fast, bear with me. Here's the energy level. Ground state, 2 electrons here, 1 here. Excited state, 1 electron jumps, okay, to the next level. So now we have 2 electrons here. Let me make this closer so they don't kind of meld into each other. There we go. Now, since in the 4th p I really don't have any electrons there, there's nothing to mix. Okay, so which means that I will just go ahead and mix this, which means you're mixing 1 s and 2 of the p. Okay, that's how it's getting mixed up. And so we have the hybridized state, and again you told me that it has to be in the middle, which it is still true. So here are the new orbitals. This is called SP2 because you mixed 1s and 2p. The empty orbital is still there. That hasn't gone anywhere because it did not hybridize. Okay, so it's still there. So now with SP2, boron, actually let me write the new one over here. So when you mix one of the s with the 2p, now you actually have a lot more s character. In this first one over here, the s character was 25%. Okay, because in 4 of them there was only 1 s, but now there's 33, which means that the p got even bulkier. So which means you would have a big lobe, okay, over there. A lot of s character in it because it's 33% s now. Okay, and so it gets a little fatter, so you'll have 3 of these, okay, like this. So which means that when I start drawing out the boron, this will be a lot fatter. And again, the hydrogen is the same, 3 hydrogens. H, H, H. All looking fantastic. And what is the AX formula here? AX3, the geometry is trigonal planar. The shape is also trigonal planar because they're all atoms there. There's no lone pair of electrons. And bond angle is 120. Perfect. So again, the properties of borane itself did not change. Okay, the properties remain the same. The only thing that changed is how we look at the bonds. SP, Be, H2. Beryllium is 2s2. Again, energy diagram. Closer. Nothing there in the ground state on the p orbitals. And now in the excited state, you will have the 1 electron. And again, you have hybridization of 1 of the s and 1 of the p. So in the hybridized state, you'll have 2 new orbitals and then 2 of the old ones. Don't forget these ones, okay? Make sure you draw these out too, because they didn't go anywhere. So now you have 1 s and 1 p, which means that you really have quite a bulky looking p orbital because it's a 50-50 character of s and p. So beryllium here now has these 2 lobes, and then we have the 2 hydrogens on the side. AX formula is, geometry is linear, and then shape is also linear. Bond angle 180. these things that I'm writing here for you, the AX2, AX3, AX4 that we did, these are the properties of the hybridization. If you remember these, then that's really all you need, okay? I'm going to borrow this chapter, if you don't mind, because in the PowerPoint and maybe in the chapter summary also, okay, I have given you, most likely, not most likely, I'm sure, okay, is there's a nice table here, okay, for you to look at. It has the hybridization in there as well. So wherever you have AX4 geometry, you're going to have SP3 hybridization. Wherever you have an AX3 geometry, you will have SP2, so on and so forth, okay? So it becomes, life becomes a lot easier, okay, when you just change your perspective a little bit and start looking at it differently, okay? All right, so now, are we okay with all of this? Should we do some examples? Yes? Okay, let's do some examples and see if we understand everything. And this is the best approach, okay? What I'm giving you right now, this is the best approach for it. So let's say you have ammonia, NH3. Right now, the kind of questions I will ask of you when you do hybridization is, here's a molecule, what's the hybridization on the central atom? It's only the central atom, please, okay? Nothing to do with the terminal atom. So what's the hybridization, what's the bond angle, such and such, okay? But the first thing you always have to do is, not the energy chart, the first thing you have to do for any structure is the Lewis structure. The Lewis structure, the Lewis, okay? If you don't have your Lewis structure correct, everything else is going to be wrong, okay? Because in the Lewis structure, you get to see all the valence electrons, all right? So that's really important, and you can see that, okay? For the last 2 chapters, for everything we have done, your Lewis structure is the key thing. That's the Lewis structure. From the Lewis structure, then you can derive your X formula, okay? So the X formula here is AX3E. How many electron groups do I have? Electron groups around the central atom, 4. Okay, and as soon as you know you have 4 electron groups, you have 3 atoms and 1 lone pair. Okay, so you have 4 electron groups, so which means that your geometry is tetrahedral. Don't forget, okay, 2 things, geometry and shape. Okay, the shape comes from the number of atoms, and geometry comes from the number of electron groups, okay, you have around here. So keeping in mind that you have 3 hybridization, SP3, SP2, and SP, okay, this is AX4 and all combinations of AX4, SP2 is AX3 and all combinations of AX3, and SP is just AX. (109), 120, 180 bond angle. The shape of the molecule will depend on how many atoms you have and how many lone pairs you have. Okay, what's my hybridization here then? Yes, one.
Did you forget next to the AX?
Thank you. Otherwise it will be diatomic. It's true. Okay. So for ammonia, what's my hybridization? Look at the X formula and then see which one it falls under. SP3. Okay. H2O, water. And I'm taking those small molecules that you've dealt with before because those are the common ones. Oxygen in the middle, hydrogen, hydrogen, and that's the Lewis structure for water. I know that's an easy one for you to do. And so then this is AX 2E2. So what's my hybridization on oxygen?
SP3.
Here's the Lewis structure. What's the hybridization on carbon here? X formula first. AX, 1, 2, 3 groups around, so AX3. So which means hybridization is? It's as simple as that, okay? Don't make it complicated.
Wouldn't NH3 be SP2?
NH3 will not be SP2 because of the lone pair of electrons.
Oh.
Okay, yeah, you have 4 electron groups. That's why you write the AX formula, okay?
Oh.
That really helps. How are we doing? Good? Okay, so that's where I'm going with this, okay? That's what you need to know. So the worksheet that you had from before, this is like the ultimate. You have all the molecules here, you can do everything in here. So what you did before was write Lewis structures, and then we took it to the next level. We did the AX formula, we did the shape of the molecule. Now what you will do, the last thing, okay, on this one that you should do is write the hybridization, okay, on each of them. Okay, that's how you should do. So if you have this worksheet with you and you want to take it out for a second, for question number 1, which is CF4, okay, CF4 is like CH4, which we did over there, so that should be, it should be SP3, okay, because that is, carbon has only 4 electrons, so 4 electron groups. BF3 is on the board because that's also BH3 in a way. Carbonate ion is this, 2 minus, so this one should be SP2, right? So that's AX3. Okay, that's how you should do it, and that's how simple you should keep it also. Okay, don't make it more complicated than that. For the diatomics, like for number 8 for oxygen, it doesn't matter. Okay, because diatomics will not have this, they have simple overlaps. So here's what you have to do for me, okay, when we get into all of this, is in some cases you will also have to tell me what kind of overlap it is, okay? All right, which we'll deal with in a second. Are we good with this? Because I need to take it to one other level, and then we'll stop from there. Good. In some cases, we start getting a little bit more complicated. Okay, so for example, when you have something like this, carbon over here, and carbon that you had at CF4, carbon here with the CF4 was SP3, but the carbon here with this carbonate was SP2. So how does this work? Okay, with the SP2 carbon over here and then SP3 carbon here, it means that things are a little bit different. Okay, so I'm going to go ahead and take this molecule for you because this is easier to understand and see what's going on. Okay, it's the same kind of thing, except I've replaced oxygen with the CH2 there, okay, with the carbon and 2 hydrogens. Now I'm going to go ahead and draw the same energy diagram I did before. Okay, so that's nothing new for you now. This is energy level here, and now my central atom is carbon. So 2 here and 2 electrons over here, that's the ground state. Nothing has changed there. The excited state also, nothing has changed, where you have 1 electron jumping to the next level. Now the hybridization is going to change, okay? Because over here, this carbon is AX3. So if it is AX3, it is supposed to be SP2 hybridized. So if it's SP2 hybridized, it means this is all I'm mixing. 1s and 2p. That's all I'm mixing. I'm not going to mix this one. So this electron is going to remain by itself, okay, when I do the hybridized. So here is the hybridized state. I have 3 new orbitals from mixing these 3, and then 1 electron, poor thing, remaining by itself. That did not hybridize. So now, when I draw this carbon out, it's not going to look like what we had before with the other carbons. So this carbon now has the 3 hybridized orbitals, which is a little bit fatter of the orbitals, okay, because you have the S character in it. And then you will also have this P that's left behind, which is your traditional dumbbell, which does not have any S character in it. Good? You also have a second carbon. This carbon right here, this is also AX3, this is also SP2. So which means that I can draw the second carbon here, same thing, 3 of these ones, and then 1 of the normal dumbbell shape. If you have a different color, it will really help, because sometimes our drawings are not all that clear. So even with a pen and pencil will work. And then of course I have the 4 hydrogens, which the 4 hydrogens will be here. The red one is the p orbital that's remaining behind. The p orbital is like this, so what it does, it kind of just overlaps on itself, okay, and gives you a new bond, all right? So it's not the 2 things that are overlapping to give 2, it's just 1 orbital, okay, because each of them has an electron, the p electron that's remaining over here, so that's still there. So this is going to, where's my red pen? That's going to overlap to give you the new bond. So now that you have 2 different kinds of bonds over here, there is a different name for these 2 bonds so that we can differentiate between the 2 bonds, all right? So the black ones here that I've drawn on the board, the black ones are called sigma bonds, sigma, and that is represented by that symbol, okay, the O. Sigma bond. Sigma bond is the hybridized bond. The red one, which is the unhybridized p orbital, that's called the pi bond. Pi is the normal symbol that you know of. So which means that when I'm looking at the structure right now, let me draw it again so it just looks a little clearer. This is what I have. Can you tell by looking at these 2 bonds which one is pi, which one is sigma? No, and no one is asking you to do that, okay? We just want you to understand that one of them is sigma, one of them is pi. Okay, that's all there is required, so you don't have to worry about anything else. So here when I ask you, show me the bonds over here, what are the overlaps that are going on in this structure, this is what you will do. Carbon here, these 2 bonds, remember these ones over here, these 2 are sigma bonds, okay? So this is a sigma bond, this is a sigma bond. What is the hydrogen again? Hydrogen is just S. Okay, just S over here. So which means that the overlap that's going on between the hydrogen and the carbon is S and sigma. Good? The overlap that's going on between carbon and carbon, one of them is a sigma-sigma overlap, and the other one is a pi-pi overlap. Or you can also say it's SP2. Okay, so for example here, you can say it's S and SP2 overlap, depending on what the question is like. Sigma bond just signifies it's hybridized. It doesn't tell you whether it's SP2 or SP3, so you have to know that, okay, whether it's SP2 or not. So here it's SP2, this is a better answer than sigma and S, okay? But if a sigma is given, then it's easier. You don't have to worry about SP2 or SP3. Good? Sorta, kinda. Okay, all right. So now let's look at the carbonate ion again. Hybridization on this carbon is SP2. So this is sp2. The overlap between carbon and this oxygen is sp2. And what's the orbital coming from oxygen? The orbital that's going to overlap from oxygen. You can look at the periodic table if you want. P. Okay, because it's in the P block. So sp2, P overlap. That's what's going on there.
Oh, okay.
Now I understand what you're asking. So sp2 and oxygen here also is going to be sp2 and a P overlap. Okay, that's what's going on there. Good? Okay. Now, when you have carbon, you can also have carbon with a triple bond. So that was carbon with a double bond, but if you remember this Lewis structure that we drew out before, a long time ago, HCN, hydrogen cyanide, here carbon has a triple bond, all right? So what's the hybridization on carbon here? SP, right? Because the geometry is AX2. Okay, so yeah, that's okay. So now here the hybridization is SP hybridization. So not wanting to draw all of this out again, with SP2 you mix these three. So with the SP hybridization you would just mix the two. Okay, that's all, which means that you will have 2 of the P remaining. So if you have the 2 P remaining, how many pi bonds do you have now? 2 pi bonds. Okay, so which means that in HCN you have 1 sigma bond and then you have these 2 pi bonds. Okay? All right, so let's take this one step further. CNH. So here we have an SP overlap between hydrogen and carbon. And between carbon and nitrogen it is SP and P overlap. And you also have 1 sigma bond and 2 pi bonds. That's how it works out. Good? At this point, this is all I need you to know. Okay? And again, the way you will work this is backward. All right? Which means you will do the X formula first. Once you have the X formula, then you will figure out what the geometry is, then you will figure out what the hybridization is. Okay? And from there, you will figure out how many pi bonds, sigma bonds you have, and that's all you need to know. Okay? At this point. There's a little bit more in there, but we don't have to worry about it. Okay. Any questions at this point regarding hybridization? The only way you will know this is when you practice. Okay, if you go on the Blackboard homework, you will find there is one other separate homework for valence bond. Okay, because sometimes I get to cover it, sometimes I don't. But this time I did, so I've made a separate homework, okay, for it. So practice on there and see if you understand the concepts, okay, of how these things overlap and how they mix up. That's about all that you need to know for hybridization. There is a third theory. Actually, let me tell you one more thing before I go to the third theory. All of this that we've done so far, this is all based on 4 electron groups, okay, which means that this is all based on the octet. The only thing we have done, which is with incomplete octet, was BH3, okay, with boron, because boron has only 6 electrons, okay, so that's incomplete octet, but we didn't take more than 8 electrons here, okay, but we know that we have molecules that have expanded shell, okay, so for example, you have PCl5, you have SF6, which is AX5, and you also have AX6. Okay, you have these geometries as well, okay, available to you. So where do you think the extra X is coming from then? That was, where did those electrons go? The extra electrons? Into the D shell, right? Into the D suborbitals, that's where the extra electrons went. In fact, those are the only elements that are capable of having an expanded shell because they have the d orbital available, okay, to them. That's why you start only from the third row, okay? So everything below that can have an expanded shell. So in this case, you have AX5, AX6. These also will have hybridization, okay? And the way the hybridization works is you still have the SP3, no problem, but now because you're involving the d orbitals, you got to start mixing the d in there too, okay? So the way you mix the d, here you have 1 and 3, 4, which means 1 is remaining, so you just add 1 d orbital to mix, okay? And then in here you have SP3, that's 4 orbitals, and then you'll have d2. So that's a total of 6 orbitals that are mixing. Here you have a total of 5 orbitals that are mixing. Okay, so for expanded shell again, don't go further than this, okay, because then it gets more complicated. If you remember the shapes of D, they were pretty complicated shapes, okay, with the flower and whatnot. So which d orbital is mixing? I don't know, okay, and I'm not an inorganic chemist to go into that deep with it, but it gets more complicated, okay, because then you have to figure out which of the, the 5 orbitals is mixing, how will the shape look like, and things like that, okay? But at this time, you can just limit it to this, and this is all fine, okay? So maybe for your homework also, this should be enough, okay? Good? All right. So we'll stop here as far as the exam is concerned. The last theory that's in the textbook is called the molecular orbital theory, okay? And the molecular orbital theory is like the ultimate, okay? That's it, okay? There's nothing better than that right now. And the molecular orbital theory will explain everything that you ever wanted to know about bonding, okay? Which the mystery will be revealed to you, I guess, in another class, because we're not revealing it here, okay, for you. So in another class, some other time. But in any case, that's the last theory that's remaining. So I'm going to stop right here. Let me give you a little review about your final exam, okay, and stuff. And I have to give your exam back as well. So